Hey everybody, it's Miss Berry. In this video, we are going over section 4.3, which is called multiplication rules for probability. We're going to get two more formulas in this section, and they're going to feel kind of similar to the formulas or to the formula that you saw in section 4.2. So make sure you have a pencil and a piece of paper, something to write with so that you can get the formulas down, and we'll get started. Before we begin, I need to give you a definition. So our first new vocabulary word that you're seeing here is independent events. We say that two events are independent when the occurrence of one event does not affect the probability of the other occurring. So this would be like the probability that it rains and the probability that you get Taco Bell for supper. Right, so those two events have no effect on each other. So just a more informal version of that definition is what you're seeing down there at the bottom. So whenever two events are independent, this means that knowing that one event has happened gives us no information about whether the other event will happen. Right, so if you know that one thing has already happened, that has no bearing on whether the second event will happen or not. So if you know that two events are independent, then you are allowed to use this multiplication rule, right? And so you might call this the AND rule, right? So just like how we called the formula in the last section the OR rule, you might call this one the AND rule, right? That's sort of like the key word that you're going to look out for in those word problems is the word AND. So if you see that it's a problem that says something like, what is the probability that you are randomly assigned a doctor who is a general practitioner and is under the age of 45? I think that was an example that we saw in the last section. So if you see that word and in there, that's going to be a clue to you that you might be able to use this multiplication rule. And of course, before you decide whether or not you're going to use the multiplication rule, you do need to check that the events are independent. All right, so here we have the multiplication rule. Let me switch over to my little laser. All right, so the multiplication rule says if you have two events that are independent, then the probability of E and F is equal to the probability of E times the probability of F. So very straightforward, very simple formula. All right, so we're going to calculate some probabilities in just a minute, but before we do that, let's practice with just figuring out if two events are independent or dependent. All right, so if the events are not independent, we would say that those events are dependent. The knowing whether one event occurs does affect the probability of the second event occurring. All right, so part A, forgetting to set your alarm and being late to class. What do you think? Is that independent or dependent? That would definitely be dependent, right? So you were late to class because you did not set your alarm. So those two events depended on each other. All right, our next one says Rob picks up McDonald's for lunch and Jose wins the lottery. Do you think those events are independent or dependent? Yeah, I think those are independent. I don't think I don't think what Rob gets for lunch could have any effect on whether or not Jose wins the lottery. All right, and then part C, being a math major and taking calculus 3. Do you think that one of those events depends on the other? Absolutely, right? Like the reason that you're taking calculus 3 is because you're a math major, right? So those are dependent events. All right, and then lastly, making a 100 on your stats exam and then taking an Uber home from a concert. Do you think that those two events could have any effect on each other? No, right? So those are independent events. Okay, so now that we have introduced the idea of independent events and dependent events, I'm going to next talk about whenever you are calculating probabilities where you have to make choices or make selections. How do you know if those events or those choices or those selections, how do you know if those are independent choices or dependent choices? All right, so here's an example to help you get a solid understanding of what a dependent event looks like versus an independent event. And sorry if I'm a little echoey. I'm in my living room and it's a little echoey in here. All right, so here's your scenario. You're going to suppose that every day when you come into class, your teacher is going to take a jar that she has on her desk and it's got a bunch of little tiny pieces of paper on it. And on those papers, little tiny pieces of paper, she's got all of her students' names. All right, so every day, whenever you come into class, your teacher is going to reach into her jar. She's going to pull out one student's name, and that student is going to pass out the papers that day. Okay, so there's two ways that she can make this selection. She can choose students with replacement or choose students without replacement. All right, so let's talk about what each of those is going to mean. If she chooses students with replacement, then that means that every day your name is going to go back into the jar and you could get chosen again tomorrow. So let's say that Jim gets chosen today. Well, after the teacher pulls out Jim's name and says, okay, Jim, today's your turn to pass out papers, she's going to put Jim's name back into the jar, and it's possible that Jim could get chosen again tomorrow. Now, if she's choosing students without replacement, then if you get chosen today, your name is getting taken out of the jar, and you cannot be chosen again tomorrow. All right, so if you are choosing students without replacement or making choices without replacement, then the total number of names that is in the jar changes. All right, so when we're choosing students with replacement, when we're putting those names back into the jar every day, the total number of names that's in the jar never changes. Whereas when we're choosing students without replacement, every day the total number of names that's in the jar is going to change, right? So every day there's going to be one less person in the jar to choose from. All right, so we would say if you're choosing students or making any kind of choice with replacement, then that's an independent event. Whoever you choose today has no effect on who gets chosen tomorrow. Okay, so those would be independent events. The choice that the teacher makes every day is an independent event. It does not have any effect on tomorrow's choice. But if you are choosing students or making choices without replacement, then those are considered dependent events because every day the total number of names in the jar changes. And if you didn't get chosen today, it's more likely that you're more likely to be chosen tomorrow, right? Because there's less people to choose from. All right, so if your total is changing, that's a dependent event. So if your total is changing every time you make a choice, then that's a dependent event. If you're doing with replacement and you're putting that name back into the jar or putting that coin back into the jar, putting that marble back into the jar, whatever it is, and the total number of items is never changing, then that's an independent event. All right, so this is one of my favorite problems. I really like this problem. Hopefully you all have at least heard of the game Clue. Clue is a board game. You have to deduce 3 details surrounding a murder. So in the original game of Clue, the guilty person can be chosen from 6 people, 6 weapons, and 9 rooms. So if you remember, there's like Colonel Mustard and Professor Plum and Scarlet and oh gosh, what was the green guy's name? I can't remember now. But there were 6 people. There were 6 different murder weapons. So there's like a rope, a knife. Um, I'm just looking up the characters. Colonel Mustard, Mrs. Peacock, Mrs. White, Mr. Green. Okay, that was like the easiest name. Okay, so 6 people, 6 weapons, and then 9 rooms. I remember there was like the study, the conservatory, the kitchen. Um, so let's suppose that you're in the middle of the game, okay, and then at one point during the game, you have on your little card, your little clue sheet, you've narrowed down the possibilities to 4 different people. So you started with 6 possible people. So you started, sorry, I had to pause the video. So you started with 6 people, you've narrowed it down to 4 people. You started with 6 weapons, now you've narrowed it down to 2 weapons. And then you started with 9 rooms and you've narrowed it down to 3 rooms. And the question is, what is the probability of making a random guess of the guilty person, murder weapon, and location from your narrowed down choices and your guess being correct? All right, so we're supposed to write our answer as a fraction. All right, so we are making 3 choices. Okay, so we are looking at our 3 choices that we have to make. We have to choose a person, a weapon, and a room. All right, so when we're thinking about how are we going to choose, right, we're looking at our narrowed down possibilities. We can choose from 4 people, 2 weapons, and 3 rooms. All right, so since we've been talking about independent, dependent, we should probably bring that up here. All right, so do you think that these events, the events being the choices, we have 3 choices that we have to make, so those individual choices are each considered an event. So do you think the choices are independent? Does one detail of the murder have any effect on another detail of the murder? Definitely not in this case, right? So these events are definitely independent because one detail of the murder does not have an effect on any other detail of the murder, right? So the only way that I was thinking that these could be dependent is if you had some kind of extra knowledge about, that maybe Professor Plum never uses the gun, right? But we don't have any kind of extra information like that, so there's no way that we could um, there's no way that one choice that we made for our person could have any effect on the choice that we make for our weapon and for our room. All right, so just to remind you of our probability rule for independent events, we know that if we are looking for the probability of E and F, that as long as those events are independent, then you can just multiply their individual probabilities together. All right, so we are looking at the probability that we have a correct guess, which is the same thing as saying the probability of choosing the correct person and the correct weapon and the correct room, right? So you could rewrite this in the and format. I'm just writing it in the sort of abbreviated way since I don't have much room. All right, so if we make the correct guess, then that would imply that we've chosen the correct person, the correct weapon, and the correct room. So we can multiply each of those individual probabilities together. All right, now we have to assume that while we're playing the game, because it says at one point in the game we've narrowed down the possibilities to 4 people, 2 weapons, 3 rooms, we have to assume that we've done all that correct, right? So we're going to go ahead and make the assumption that we have correctly eliminated the other choices and that there truly are only 4 choices left for people, 2 choices left for weapons, and 3 choices left for rooms. All right, so the probability of choosing the correct person, there's only 1 out of those 4 people who actually committed the murder, right? So we have a 1 out of 4 chance of guessing correctly. For the weapons, we've narrowed it down to 2, so we have a 1 out of 2 chance of guessing correctly, right? So only 1 of those 2 weapons is correct. And then for the rooms, we have a 1 out of 3 chance of guessing correctly. All right, so these are easy. Multiplying fractions is a lot easier than adding and subtracting fractions. you just multiply the tops and multiply the bottoms. All right, so 1 times 1 times 1 is 1. And then 4 times 2 times 3, that would be 8 times 3 is 24. All right, so that's going to be 1 over 24. Sorry. Okay, there we go. 1 out of 24. All right, so we have a 1 out of 24 chance of guessing correctly. There are 20, or another way of saying that is that there are 24 possible combinations given what we've narrowed it down to. So based on our narrowed down options, there are 24 possible combinations. Okay, here we have another slightly more complicated problem. It says Comcast internet service is terribly unreliable. On any given day, there's a 35% chance that the internet connection will be lost at some point in the day. Read that carefully now. 35% chance that the internet connection will be lost. Okay. What is the probability that the Comcast internet service is not broken for 6 days in a row? All right, round your answer as a decimal. Write your answer as a decimal, rounded to 4 decimal places. All right, so let's assume right off the bat, let's assume that the events are independent. So every day we'll assume is an independent event. So we're assuming that the internet connection be lost one day. So say like you're during lunch today, the internet connection is lost for a few minutes and then it comes back on. Let's assume that that has no effect on whether the internet connection is going to be lost on any other day. All right, so just to remind you of our rule for independent events, our multiplication rule for independent events, we can multiply the individual probabilities together as long as the events are independent. All right, so the probability that the connection is not broken for 6 days in a row, that's the same thing as saying that the probability that it's not broken on day 1 and it's not broken on day 2 and it's not broken on day 3 and day 4 and day 5 and day 6, right? So we are multiplying those individual probabilities together and we're doing that 6 times in total, right? All right, so we're looking at the probability that the internet connection is not broken. If there's a 35% chance that the internet connection will be lost, so we'll say is broken, so there's a 35% chance that the connection will be broken. What is the probability that it's not going to be broken? All right, so if there's a 35% chance that the internet connection is going to be lost at some point in the day, what's the what would be the probability that it's not lost or not broken? That would be 65% chance, right? So we're going to multiply 0.65 times 0.65 times 0.65 6 times, right? So 1 for each day. All right, that's the same thing as saying 0.65 raised to the 6th power, if you want a little bit easier way to plug that in. So 0.65 to the 6th power. And if you multiply that out, that comes out to 0.0754. So if you're thinking about this in percentages, that's about 7.5%. So you have a 7.5% chance of going 6 days in a row without losing your internet connection. All right, so the last thing we have to talk about is if you know that 2 events are dependent, then you have to use something called conditional probability. All right, so conditional probability, we have a new symbol here. This long straight line means given. All right, so if you see that long straight line, that means the word given, G-I-V-E-N. All right, so it says the probability of F given E. That means the probability of some event F occurring given that you know that some event E has already occurred. A really good way of thinking about this is imagine that you are walking into a coffee shop and you're supposed to be meeting, let's say you're supposed to be meeting someone that you've never met before, but you know that they have long hair. Okay. So you walk into this coffee shop, um, and maybe there are two people there. One has long hair, one has short hair. All right, so if you know that the person that you're looking for has long hair, then you're more likely to choose the correct person, right? So you're not going to walk up to the person with short hair. You're going to walk up to the person with long hair. So if you already have some prior information about um, some events that are going to be occurring, then that can help you get a more accurate idea of the probability, right? So conditional probability is calculating probabilities when you know that some event has already occurred. And again, it just helps us update probabilities based on new information. Helps us get like a more accurate idea of the probability. All right, so whenever we are calculating conditional probability, there is no button in our calculator or anything. We have to manually do this division. All right, so it says the probability of F given E is equal to the probability of E and F divided by the probability of E. So I want you to notice that whatever comes after the given line always goes to the denominator. Right, so whatever event comes after the given line, that's always the event that you're going to put in the denominator. And then for the top up here, so for the numerator, the probability of E and F is the same thing as probability of F and E. All right, so just a heads up, sometimes they like to write them backwards in the homework. Just know that those mean the same thing. If I say apples and oranges, that's the same thing as oranges and apples, right? So E and F is the same thing as F and E. Sorry if y'all hear that, that's my children being dramatic in the background. All right, so if we're reading this out loud, again, we would say the probability of F given E. All right, so I really like to use tables whenever we are calculating conditional probability. So that is what I would advise you to prepare for the exam, is to see a table for the conditional probability problem. All right, so it says the following table summarizes data collected at the beginning of a semester from some statistics students that I had. All right, so I asked them, what year are you? Freshman, sophomore, junior, senior, and then do you live on campus or off campus? All right, and then we've seen this table before, so you may remember the totals. And if you don't already have the totals sort of in your head, take a second, pause the video, and calculate those totals. So you're going to add up all the people that live on campus, all the people that live off campus, and then add up the seniors, the juniors, the sophomores, and the freshmen, and then get the overall total. All right, so there are my totals, if y'all remember those from the last time we used this table. And the question says, what is the probability that a randomly chosen student lives on campus given that you know already that this student is a sophomore? All right, so on campus, given that they're a sophomore. All right, so I'm going to use the following abbreviations. For on campus, I'm going to use on. For off campus, I'm going to use off. Freshman, I'm going to use F. Sophomore, I'll use SP. Junior, I'll use J. And then senior, I'll use SR. All right, so if we're looking at probability that they live on campus, given, so we see that word given, remember that means the long straight line, that they live on campus, given that they are a sophomore. All right, so we're going to use our formula. So we're going to apply our formula, which says that this is going to be equal to the probability of living on campus and being a sophomore divided by whatever comes after the given line, so the probability of being a sophomore. All right, so probability of living on campus and being a sophomore divided by the probability of being a sophomore. All right, so let's look at just the numerator first, on campus and sophomore. All right, so we're looking at if you're looking at the word and, you're thinking of the intersection when we're looking at table problems. All right, so on campus, that's this row. So on campus and sophomore, there were 10 kids that were on campus and sophomores. So 10 out of 82 were on campus and sophomores. Sorry, I didn't mean to pop up the bottom one also, but probability of being a sophomore, we had 33 out of 82 students that were sophomores. So all of our sophomores. Now I'm going to ask you to remember some stuff from algebra. Usually people remember this. If you are dividing two fractions, we have to do keep, change, flip. All right, so keep, change, flip. The fancy way of saying that is multiply by the reciprocal. Right, so you keep the top fraction the same, you change that operation to multiplication, and then you flip that bottom fraction. So keep the top the same, change the operation to multiplication, flip the bottom one. And when you do that, you're going to have this nice little cancellation happen. All right, and then you're going to be left with 10 over 33. So 10 over 33. All right, so that's our probability for selecting a randomly chosen student who lives on campus, given that we knew that the student was a sophomore. All right. Similar, or same table, sorry, same table. Let me get the totals on there. Okay. Now we're looking at what's the probability that a randomly chosen student is a junior, given that you already know that they live off campus. All right, so probability, there's all my abbreviations again. All right, so probability that they're a junior given that they live off campus. So again, there's the word given. What comes after that is what comes after the straight line, the long straight line. Okay, so junior given off. All right, so junior given off campus, the formula says we're going to do, that's the probability of being a junior and living off campus divided by the probability of whatever comes after the given. So that's off campus. So probability, excuse me, of junior and off campus divided by the probability of living off campus. All right, junior and off campus. Let's see, junior and off campus, that was 10 out of the 82 students were juniors and off campus. And then for off campus, let's see, we had a total of 51 out of 82 that lived off campus. All right, so 10 out of 82, we saw that, 10 out of 82, and then 51 out of 82 for the denominator. Now keep, change, flip. That becomes 10 out of 82 times 82 over 51. Notice that the 82 is canceled. That'll happen every time, right? So you can count on that happening. If you want to not even keep, change, flip, if you just want to say, okay, it's going to be this numerator over this numerator, that'll work every time. You can do that. All right, so that simplifies to just 10 over 51. All right. I think this is our last problem. It says out of 467 applicants for a job, we have 118 that have over 10 years experience. I'm going to use just the word over for that variable to represent that variable. 81 of our applicants have a graduate degree. And then 67 of our applicants have over 10 years experience and have a graduate degree. Right, the question is, we got a lot of numbers there, right? So we're going to have to figure out what we're going to use. The question is, what is the probability that a randomly chosen applicant has a graduate degree given that they have over 10 years of experience? All right, so let's write that out in our little abbreviations. So graduate degree given over 10 years experience. So graduate degree, long straight line, over 10 years experience. So the word given again is represented with that long straight line. All right, so applying our conditional probability formula, we would say that this is equal to the probability that a student, or excuse me, that an applicant has a graduate degree and over 10 years experience divided by the probability that they have over 10 years experience. So that's what comes after the given. All right, so probability of having a graduate degree and over 10 years experience divided by the probability of having over 10 years experience. All right, so let's fill in those probabilities. Looking at the numerator, we were told that 67 applicants had both a graduate degree and over 10 years experience. So that's going to be 67 out of our 467 applicants. And then for over 10 years experience, we would say 118 out of the 467 applicants had over 10 years experience. All right, so 67 over 467 divided by 118 over 467. So keep, change, flip, or just think, okay, it's going to be this numerator, the numerator from the top over the numerator from the bottom. All right, those 467s cancel, and you're left with 67 over 118. Okay. If you have any questions from this section, please let me know. Otherwise, I'm going to see you guys in our last section for chapter 4, which is about combinations and permutations. Thanks for watching.